Connecting and calculating three-phase auto transformer banks with single-phase buck boost multi-winding isolation type transformers. What the heck is that? Well, I'm glad you asked. A buck boost transformer looks like this. It's a multi-winding transformer that typically has identical primary and identical secondary windings in its construction. It's usually isolation, meaning there's no electrical connection between the primary and the secondary windings. And the VA of the entire transformer, if divided by 2, would then give us the VA rating of each of these individual windings. Now, if we had 3 of these transformers, we could make a Y auto transformer bank for 3-phase. If we had 2 of these transformers, we could make an open delta 3-phase auto transformer bank. When we're connecting isolation type transformers into auto configuration, we will find that the kVA that they are able to provide to a load is increased significantly. And so because of that, the total bank kVA must be calculated for each connection. Now, before we get too far, we need to have a good idea as to how the connections work on a buck boost transformer so that we can start determining what is necessary for the 3-phase bank connections. Here's a typical buck boost transformer. We have 120, 240 listed. That would be the windings in either series or parallel. And then we have 6120, and that would be the secondary windings connected in either series or parallel. Remember, this entire transformer, if it was rated 1000 VA, each one of these individual windings would have a VA rating of 500 VA. Now let's take a look at the different connections that we could have when it comes to an isolation type connection. Well, we could do the primary in series and the secondary in series. That would be 240 source, 120 volt load. We could do them both in parallel, 120 volt source, 60 volt load. We could do them a mixture. So series for the primary, parallel for the secondary. And finally, we could do parallel on the primary, secondary being series, and no voltage being changed, simply isolation from the source to the load. Now we can also connect these in auto configuration. And auto configuration means that we're going to have a series connection between the primary and the secondary. It's going to go from here to here, and that connection is going to remain consistent and the same for every single auto transformer connection we do with a buck boost transformer. So let's take a look at the different options that we have. We could put all of the windings in series, and that wire right there is what I was referring to that connects from here to here. If we put the primary in series and the secondary in series, then I have a total source voltage that I could use of 360, and I could drive a 240 volt load. We could also have a source voltage of 180 if I chose to do all of them in parallel, and the primary having a load voltage of 120. Or rather the H winding, shouldn't say primary, the H. What if I did parallel on the H windings and series on the X windings? Well, these are 60 volts apiece, which means 240 volt source, 120 volt load. And finally, we could have a 300 volt source, 240 volt load. And why on earth would we have 300 volts? Remember, there are voltages outside North America that are much different than what we have for our nominal 3-phase voltage values. And because of that, we need to, at times in the industrial side, choose what type of transformer is necessary to supply voltage to a non-conforming piece of equipment. So if I have a piece of gear that comes in that's rated for 300 volt 3-phase, I'm going to need to use an auto transformer of some sort to get that non-standard voltage. Now, there are more connections. Well, not really different connections so much as different termination points for the load. But look at how many different connections we could possibly have for this one transformer. And so you get to see the ramifications of the manufacturer providing a multi-winding transformer because it can service so many different sources of supply and also so many different load voltages. This is a diagram from one of the main manufacturers of transformers here in North America, just showing all of the different connections that we can do for a typical buck boost transformer. So this is very much a common application when we are attempting to change the voltage for an individual piece of equipment. Well, let's do a few examples with buck boost and we'll do some calculations and connections together. The first one we're going to do is a Y connection. The Y connection is going to use three 113.5 227 to 60 120 volt buck boost transformers. I've got the diagram of the transformer here, and it's going to have a rating of 5 kVA. Now we've got a source of 208 volt line, 120 volt phase, and a load of 600 volt, 347 volt phase, and that's three phase. We're going to do a Y connection, which means we should arrange our windings for the individual three transformers, something like this, so that we can start to have context for where the different values are going to be. Now, for my installation here, I'm going to choose to put the X windings here and the H windings here, and you'll see why that is as we go along. Now, there is no standard for when do the X windings have to be at the star point or when do they have to be out here at the outer reaches of the star configuration. It's something that you will see as you're building the circuit where it is necessary to make that star connection. So first off, I'm just going to write in here the voltages of my X windings. Those are the low voltage, and the voltage ratings for my H winding, which are the high voltage. What we want to do is connect this source to service the load, but remember it's a Y connection, which means I really only need to know the phase voltage values. The first thing we should be aware of is that the phase voltage of 120 needs to be present as well as a phase voltage of 347. Now, with this particular installation, we know that since it's an auto transformer, the X and H winding is going to have to connect together in series. So I'm just going to put that in here because we know it's kind of a foregone conclusion. It needs to be there. Now, the low voltage phase value from here to here has to be 120 volts for our source. The low voltage will be from somewhere in the midpoint to the star. So I'm just going to put a little dotted line here and another dotted line down here. We know that this must be 120 volts. I need 120 volts for my source. And this one from here to here must be 347 volts. I need that for my load. And so based on that information, I can start to piece together what the winding connection must look like. 120 plus 227 gives me 347. And so what this tells me is that I have a star connection here and then a series connection for all of my other windings. And that's because 120 volts plus 227 equals 347 volts. So let's do that connection on every one of these windings. This is transformer 1, transformer 2, transformer 3. Once I've got them all located, now I can start looking at the actual connections. I'm just going to sketch in where the load connection would go and where the source connection would go. The source connection is the lower voltage, and really the source connection could come from either this terminal here or this terminal here. It does not make any difference, and often you'll see a line just coming from the right from the middle of the jumper. I'm just going to choose to go from here, and we're going to have to go all the way over to the source. Now we're going to do the exact same connection for each of the other transformers. So those are the 2X, there's the H winding. And finally here, there are the 2X windings, there's the H winding. Great. So now we've got the primary or supply connection completed. The next one we're going to do is the load connection, and the load connection needs to have a 347 volt value for the phase, which means we are connecting to the outer reach of each one of the star arms. So I'm going to head over to that one. This one goes all the way across and up, and this one like that. All right, so we've got 3 connections for the load, 3 connections for the source. If the load required a phase connection, we could take a 4th conductor right out of the center, and that would then be our neutral. Now, after we've got the configuration completed, we need to know what is the maximum kVA that this particular bank can supply. And at this point, we need to now have a firm understanding of what the kVA value will be of each winding of the transformer. So I'm going to look at one winding of the transformer here. One winding, we said at the beginning of the presentation, is going to be equivalent to half of the total kVA rating of the transformer. So if the transformer is rated 5 kVA, it means that one winding is rated 2500 VA or 2.5 kVA. Now with this information, now what I'm going to do is I'm going to find a series connection for somewhere in the circuit. It doesn't have to be the supply, and it doesn't have to be the load. I'm looking for a series connection between a winding and the line conductor that supplies or is being supplied. And I see it right here. I've got one high side winding, and it is in series with my 600 volt, 347 volt load. Now, we said each winding is rated 2500 VA. I circled an X winding, but really it doesn't matter which winding we're looking at, it is rated 2.5 kVA. So that then means that this winding here is rated 2.5 kVA. And I'm going to use this information along with the voltage to determine what is the maximum amount of current that this winding is able to carry. The VA is 2.5, the voltage is 113.5. So all I'm going to do here is a very simple single phase calculation. I is equal to S over E. 2500 divided by 113.5 volts. Now, what this gives me is a current value. This is the maximum current that this particular winding in the transformer bank can handle. And it comes out to 22.02 amps. Now, we can all agree this would be the line current, 22.02 amps. And if that is the line current of my load and the load line voltage is 600 volts, then we should be able to calculate what the total available kVA is for this 3-phase auto transformer bank. So in order to do that, I'm going to do this calculation here. S total is equal to E line times I line times root 3. Well, E line is 600 volts. I line is 22.02. And obviously root 3. When I plug it all in my calculator, so 600 times 22.02 times square root of 3, I get a total VA capacity of 22,883. So I'm just going to put in 22.83 kVA capacity. This is the safe capacity for this particular transformer bank rather, with a 600 volt load, 208 volt source. We can drive a 22.8 kVA load. And of course, if we wanted to calculate what that equivalent value would then be for line current on the primary, remember, kVA out equals kVA in. So you could quite easily then go ahead and calculate the primary source current here by taking the 22.83 kVA and adjusting our formula here to calculate for I line on the primary, which would be 208 volt line value. So we've got 3 transformers. The total isolation rating would be equivalent to approximately 15 kVA. However, when we connect it into auto, we get a total kVA capacity of 22.83. Let's take a look at another example. This one is again going to be a Y connection. Similar transformer, not the exact, well, no, it is, well, it's similar. Secondary's the same voltage, primary is a little bit different. We've got that diagram again here, and I've given the load voltage of 416 volts and the source voltage of 208, and we're doing a Y connection again because we have 3 of those available transformers. So first thing we need to look at is what is the connection going to look like? So I'm going to sketch it all out first, just as the individual windings. And then what we're going to do is look at the individual voltages that are necessary. So we've got 120 volt phase and 240 volt phase. So I'm going to do the same thing I did on the previous. I'm going to draw a dotted line here and here, and from the middle. Now remember, we've got a series connection that is going to connect the high and the low voltage windings together. The low voltage or incoming value of voltage is going to be 120 volts. And so that would be from here to here. So I'm just going to put 120 volts. The voltage that I need from here to here is going to be 240. So that's from here all the way up to here. Well, now that I have those 2 voltages, we can look at what is necessary for my connections on my windings in order to achieve this. Well, on the H windings, in order to get 120, I would need to put them in series. So let's do a series connection. If I were to get 240 from here to here, that would mean that, well, my series 120, 240, right? And over here, 60 and 120, this would mean that we have to have, well, let's take a look, 240 volts, 120 plus another 120. I've just done that wrong, haven't I? The 120 would be if it was in parallel. There we go. So let's correct that, shall we? Very simply, look at how elegant that is. I use a whiteout pen. So parallel. So these are in parallel, 120 volt, that makes more sense. And now the X windings are in series to give me another 120 volt, giving me a total voltage of 240. All right, so let's go ahead and connect my H into a star point here. And I'm going to connect my H and X together in series. And now we're going to connect our X windings in series. And now we're going to connect our H windings in parallel. So there's my parallel connection. All right. So now that we have all of that determined, let's complete the connections for the source and the load. For the source, I need a 120 volt phase, so it's going to come from here, and I'm just going to take it off of the X terminal. So it's going to go all the way over to my source, and it's going to be the same for each one of these. So like this and like this. Now, how did I know to put the H windings near the middle in order to have that value for the for my source or my 120 volt phase? Really, it would be up to you. Are you going to put the X windings in the point there at the star, or are you going to put the H windings? It really doesn't matter for this particular connection because they were both 120, 120 here and 120 there. All right, the second connection is going to be to the load, and that is going to require us to connect to the outer reaches of our star-connected auto transformer bank, like this, and like this. All right, so now that we have that connection completed, we can go ahead and determine what is the total kVA of load that we can drive. Now remember from the previous example, I said one winding is equivalent to exactly half of the total kVA of the transformer. So this is 2.5 kVA. The next thing we're going to do is search for a series connection. Pretty simple. It happens to be on the load side again, but this is not always going to be the case. So it just happens to be for our situation. So we know that this is rated 2.5 kVA. And we also know that the voltage of this one individual winding here is actually 60 volts. So same process as before, we are going to be taking our value of kVA in voltage to work out the rated current. What is the maximum current that 60 volt coil or winding is able to put out? So I is equal to E over S, or S over E, I should say. So we're going to take our 2500. No, I think I screwed that up yet again. It's actually, yeah, S over E. Sorry about that. So S over E, which is 2.5 kVA divided by 60 volts. And if we do that calculation, it comes out to a fairly high current. So 2.5 kVA divided by 60 volts divided by 60 volts. There we go, 41.6 amps. All right, so that would be the amount of line current that we could safely provide to our 416 volt three-phase load. Now, what is the total kVA then of the load that we could drive? Well, same as before, I line, or sorry, S total is equal to E line times I line times root 3. I'm just going to get rid of that because it looks really gross. There we go, much better. So S total is equal to E line times I line times root 3, which means line voltage 416 times line current 41.6 times root 3. Well, let's do that calculation and see what we come out with. 416 times 41.6 times root 3. I get, oh, look at that. That's kind of crazy, hey? That's 30,000 VA, 29.974 kVA. So 29.97 kVA, and this would be the capacity of this three-phase auto transformer bank. So notice we used 3 5 kVA transformers, and we are able to drive almost 30 kVA worth of load. So that's a substantial cost savings. Substantial when compared to a typical standard isolation type transformer. All right, well, let's take a look at another example. This time what we're going to do is connect a delta, open delta. So open delta requires only 2 auto transformers, and because it's connected in delta, we don't need phase values. All we need is the line voltage values. And I would say for most often, it's actually more common to see this type of connection, and it's actually easier to calculate. All right, so first thing we need to do, 208 volt source, 240 volt load. Let's sketch out our 2 individual transformers with all their windings and in an open delta configuration. So there we have the open delta configuration. I'm going to put the voltage that we require in much the same way that we did with the Y connection. So we have this. So I have a lower voltage and a higher voltage. The lower voltage is 208. So 208 volts I need present here and here. The high voltage is here, and the voltage I need for that one is 240 volt. All right, so 208 volt, it looks like I'm really restricted. I need to put them in series because each one of these windings is rated 104 volts. So I'm going to put those in series. And also, remember, we're doing an auto transformer connection, so the H and X windings right here needs to be connected also in series. All right, the next one is 1632. So I need to have 240 volts, and so we can do a quick arithmetic here and just subtract 240 minus 208 gives me 32 volts. So that tells me that here, those two windings must be connected also in series. Now that we've determined this, we can complete the remainder of the connections. So we know that this must connect together because this is the open delta connection point, the star point, or not star point, but the common point. The next step, we're going to now connect our source to the 208 volt connection points. So the first one is going to go here. The second one, I'm going to take from this center connection point between the H and the X, and it doesn't matter which terminal I take it from, right? So I'm just going to choose to take it from this one here. And finally, from the third leg right here. All right, now the load is going to be supplied, 240 volt three-phase load, and that 240 volt load we are going to have off of this point here. So I've got actually a connection that's going to come off the common point, right? This connection here connects to both the load and the source. I'm going to have a connection here from my X terminal, and finally from this one here. So now we've got our connection for both the source and the load. And now we can go ahead and calculate what is the total kVA of this particular bank. Well, again, I'm going to bring us always back to this and say, listen, remember, we have to search for a series connection, and we have to realize that that individual winding is actually rated 2.5 kVA. Well, down here is where we find a series connection. It just happens to be the same for most of these connections that we've done so far, 2.5 kVA. And we know that the voltage of this particular system is 16 volts. That's one individual winding. So we're going to do our calculation in order to work out the current. I is equal to S over E, which is 2.5 kVA divided by 16 volt. So when we do that calculation, 2500 VA divided by 16, I get 156.25 amps. And that would be the amount of maximum rated current that our load could require. 156.25 amps. Now remember, that value is not exceeding the 16 volt 2.5 kVA rating of that individual winding. So it's totally fine. Well, let's go ahead and calculate the total kVA of the system. And that would be S total is equal to E line times I line times root 3. We get an E line voltage of 240 volts, a I line current of 156.25, and of course, root 3. So let's calculate it all out. 240 times 156.25 times square root of 3. And I get, oh, look at that, 64.95 kVA. Wow, that is a whopper. So take a look. What did we use for the connection? We used two 5 kVA rated isolation type transformers. Because we connected them in auto, and because we chose to do an auto open delta connection, the increases in efficiency are monstrous. We can supply almost 65 kVA worth of 240 volt three-phase load. It's monstrous. So just be aware, massive increases in capacity are actually quite common. This is a 13-time capacity increase from 5 kVA. Well, I guess we have two of them, so 6 times. All right, well, let's do one last example. And this one again is going to be an open delta. So here's our open delta. We've got a 480 volt three-phase source, a 400 volt three-phase load, and we've got two 200 to 400 160 5 kVA buck boost transformers. We're going to connect this in open delta, which means there's a few assumptions that we can first bring to the table. First, well, I know I've got to have the X and the H winding connected together. And also, I know that I need to have this common connection up here to make my open delta sort of a pinnacle or pyramid point. All right, next step, let's take a look at the voltages that are required. I'm going to go from here to here and here. And I know that I need to have, well, this case, I've got 480 and 400. So 400 volts is going to be from here to here, and 480 volts needs to be present from there to there. So this one's a little bit different. We're doing a step down. Okay, so the X windings and the H windings. How do I get 400 volts here? Well, it looks like I need to connect them in series. So that would be a series connection. Now over here, I need to go from 400 to 480, which means I need 80 volts across these windings, and 80 volts we see identified up here. That would mean they need to be in parallel. Okay, well, parallel means I need to do something like this. All right, so now that we have the identification of the different windings in series and parallel, let's go ahead and complete the rest of the connections. So there, my H windings are in parallel, and my X windings, sorry, my H windings are in series, my X windings are in parallel, and I just screwed up that connection. That goes there. We'll just get rid of that one connection right here. There we go. So we've got our X windings in parallel and our H windings in series, and I know that I need to connect my source to the end terminals here. So first connection, there's my source, source, and source. My load is going to connect to that in-between portion between the H and the X terminals. So I know that this has to connect over to the load. And I'm going to take another connection here. And finally, from this one. All right, so now we have our connections completed. Now let's take a look at what we have for a series connection. This one's not as easy for us to identify, but don't worry, it's quite a simple process. So I'm going to look at the end of my open delta connection here. And the open delta connection, it's actually a parallel connection. And what that means is that there's actually going to be a total amount of current in this location running down this conductor that is equivalent to the current flowing through this winding plus the current flowing through this winding because they're in parallel. Parallel, the current value should add together. Now there's two ways for us to approach this. We can look at the individual voltage of each one of the windings, which is, let's see, 80 volts, 80 volts. And we can calculate the value of current that one winding will have and then multiply it by 2. Or, since we're using both of those secondary windings at 80 volts, we can take the total 5,000 VA and divide it by the 80 volts. It's really up to you. So because they're in parallel, we are doing both windings in order to work out this current right here. I'm going to choose to use both of these windings together and calculate it at one time with 80 volts. And that is equivalent to me doing this. I'm calculating the total amount of current for these at when they're in parallel, and I know that that is 5 kVA worth of S, or capacity. So current is equal to S over E. Total S, because both the windings are in parallel, is 5,000 VA. Voltage is 80 volts. This means I take 5,000 divided by 80, and we get 62.5 amps. So 62.5 amps. Now remember, where have we calculated this current? This is not the load current. This is my incoming source current. So 62.5 amps. We're going to now calculate what the total kVA capacity is of this transformer bank. And because the output VA and the input VA should be equivalent, my calculation and process does not change from the previous 3 examples. S total equal to E line times I line times root 3. In this case, E line is now 480 because the 480 is my source connection. So that's 480 volt times a line current of 62.5 amps times root 3. So we plug all of these into the calculator, 480 times 62.5 times square root of 3, and I get 51,000.9 or 51,096, 961 rather, VA. So 51.96 kVA capacity. That's insane. Absolutely insane. And so whenever we get the chance to install an auto transformer, we try to take it instead of an isolation type. There are some restrictions which you can find in section 26 under transformers that tell you exactly when and when you cannot use an auto transformer. But man, if you have the option of choosing either a auto transformer or an isolation type transformer, you are going to get some monumental cost savings by choosing the auto transformer arrangement.